This is your pre-lab video for your calometry lab. We're actually going to do two calometry labs. One of them is going to be using calometry to determine specific heat capacity, and the other one's going to be used to determine the amount of heat that is being released during a combustion reaction. But this video is going to focus on the specific heat capacity portion. Okay, so you're going to have a calorimeter, which is a device some of us are familiar with. Okay, it's going to be a metal can, right? And inside that metal can, I'm going to have some water. Okay, so I also have a thermometer in that metal can. Okay, and what we're going to do is we're going to measure how much energy is going into the water. Okay, and you're thinking, well, what do you mean by energy going into the water? We are going to have some metal samples. Okay, so we'll have metal sample here. It's just going to be a little metal cylinder. You're going to have 4 of them. Okay, you're actually going to have 4 different metal cylinders, and you're going to have all of them at 100 degrees Celsius. Right, so they're actually going to be sitting on a hot plate with boiling water, and that rapidly boiling water is going to indicate that of 100% over 100 degrees Celsius. And then you're going to add that hot metal into the water, and that of course will transfer heat into the water from the metal cylinder. Okay, I know it looks like it's coming from the outside, but it's not. It's actually, I'm just showing that I'm adding heat to the water. Now, the reason why this is important is because if I'm adding heat to the water and I know the temperature change, right, because I have the thermometer, and I know the specific heat capacity of the water, which is 4.184 joules per gram degree Celsius, and I know that I have the mass of the water, I can actually calculate how much heat went into the water. Which means if I know how much heat went into the water, I also know how much heat left the metal, because that should be the way it is, right? The metal should be providing heat for the water, so as the heat is being transferred from the metal into the water, and if I'm able to calculate the amount of heat that was transferred into the water, I am also able to determine the amount of heat that was transferred from the metal. Okay? You're going to do this 4 times with 4 different metals, and you are going to create a calibration curve. Okay? And the reason why you're going to create a calibration curve is to determine an unknown metal. So what a calibration curve is going to look like, okay, we're going to have an axis, okay. You're going to have your, we're going to have the actual specific heat capacity, okay, actual C, specific heat capacity. And then I'm also going to have your calculated, okay, from the equation, okay, and I'll show you the equation here in a minute. Calculated heat capacity, and you're going to have, 4 dots. From those 4 dots, you are going to draw a best fit line, a straight best fit line, and not freehand like I just did. Okay? And then what you will do is you'll do this process right here one additional time, but instead of using the block, you'll use an unknown metal block, okay? Or one of the 4 blocks, you'll use an unknown metal block, and you'll be able to calculate where, using the same methods you did for the 4 other blocks, 4 known blocks, you'll be able to calculate a specific heat capacity, right? So you find your specific heat capacity, say it's right here, I can then look down and find what the actual specific heat capacity is, and then when you know what the actual specific heat capacity is, you just look it up on a table, which will probably be provided on the website. Okay, and then you can identify what that metal is based on that. All right? So, as far as how you're calculating the specific heat capacity, okay, I'm going to show an equation, right? You guys know this one. Q equals mc delta T, right? That's an important equation for this, because hopefully we realize that the energy, which is Q, the Q of the water, hopefully we realize the Q of the water is endothermic, right? Because the water is going, the energy is what is being gained by the water, so that's a positive Q value, okay? Which means the Q value for the metal is negative. Okay? Now, I know this looks weird because I can have a positive Q and an equal to a negative Q. You just need to remember that the signs don't necessarily mean numerical value, they mean direction. So if we know that Q is equal to mc delta T, I can rewrite this and go the mass of the water times the specific heat capacity of the water times the change in temperature of the water, okay, is going to be equal to the mass of the metal times the specific heat capacity of the metal times the change in temperature of the metal. Okay? So here I have, sorry, this should go over here, right? Because this is this equation. This is with this equation. Okay? Now, the whole point of this is to determine this, the specific heat capacity of the metal. Okay? So obviously, I want to get Cm by itself, so I will divide both sides by mm delta Tm. So mm delta Tm, which means my specific heat capacity of the metal is going to be equal to the mass of the water times the specific heat capacity of water, which we know, okay, times the change in temperature of the water divided by the mass of the metal times the change in temperature of the metal. Okay? This is the equation that we're going to do in order to solve for specific heat capacity. Okay? I guarantee on your test there will be a test question that is related to this lab. Okay? Specifically dealing with this type of literal equation to solve for heat capacity of a metal based on laboratory data. Okay? So, you have, once you've solved for the specific heat capacity, then you can enter it into your, enter it into your graph. And then once you have it entered in your graph, you plot all four, since there's four different substances, okay? And then I will let you graph this out and draw a best fit line. And then you'll get your unknown, and you'll do the same thing that you did here, and you solve for heat capacity. And then you're going to match it up with your line to find out where your actual heat capacity is. Okay. If you want to know what your metals are to begin with, okay, I'll go ahead and tell you those. Okay, your four metals are going to be copper. You're going to have iron. You're going to have brass, which is an alloy, which does not have a symbol. Okay, so copper, iron, brass, and lastly we have aluminum. So those are going to be your four knowns, and they're actually in that number. I'm going to have 1, 2, 3, 4. They're going to be numbered. Okay, so you'll go ahead and do this 1, 2, 3, 4, depending on where your dots lie, and then based on where you did your calculations and based on the actual specific heat capacity, okay, which is something that will be provided to you, okay, you'll make a graph, draw your best fit line, and then you'll do this whole process one more time with the unknown to go back to your graph, find where it was in your calculation, and then find it on the line, and then draw down to find the actual heat capacity, and then of course look that one up too to identify the metal. Okay? If you guys have any questions, let me know, but make sure we bring closed-toed shoes, and make sure we keep if we have a way to keep our hair back, because we don't want anything to get in our face right now, okay? Since we'll be dealing with heat.